to be aware of that. And I'm pleased to introduce Dr. Greg Baiden, who is joining us from north of Toronto way in Canada. And he is the Chairman and Chief Technology Officer of Penguin Automated Systems. And he was just mentioning to us that they're in an area of Canada where they've been mining an asteroid for 70 years, if I remember correctly, which is really interesting in its own right. And Greg has been working with a number of companies, including Shackleton, who some of you may know, a former activity that Jim Caravala was pursuing, and looking at ways of doing off-world and on-world, I would imagine, mining. So let me turn it over to Greg, and thank you for joining us, Greg.
Thanks. So I want to start off the presentation, first of all, by showing you the smelter that we live around. That stack is just being torn down, actually, because we've sorted out how to keep all the materials contained. But that stack is the tallest standing free stack in the world. And it's been in place since the 50s. This area for the longest time produced 95% of the world's nickel. Through World War I, World War II, all of the new airplanes, military equipment, we were a strategic mineral in the US, and subsequently were run out of New York for quite a while, and then became a Canadian company around 1960. The work I'm going to show you today is work that I've done over my career at Inco, and I've done with a number of companies, as well as a major study that Brad Blair and I did for the Canadian Space Agency on how to mine the moon. One of my colleagues, Bill Husterlid, is now in his late 70s. He originally did a study for NASA several years ago, and then I took his study and updated it for the Canadian Space Agency so that there was a plan for strategically how to mine the moon. We in turn presented that at a number of different venues, and I had a brief interlude with Shackleton probably a few years ago, but the plan that we put together has been together probably for the last 15 to 20 years. So I'm going to just show you a little bit about Penguin. We're a small company of about 25 people, where we custom build robots and robot systems. We do strategic planning for mining companies, where we come in and look at their ore bodies and then create the telerobotic system for them to run like an automobile factory would run their operation. So if you think of a Ford or Chrysler plant where robot arms are moving around to manufacture a car from the frame through to testing it, we work on that kind of strategic planning for mining companies. Some of our work has also gotten into emergency systems, where we get called in when a mining company has a very large problem, and I'll explain one of those problems in a second. And then as we develop things for people, some of those can turn into products, and we are working with 3 companies right now, taking our core technologies and embedding them in their mining machines / robots that are going to be for sale worldwide in the next number of years. We're a private R&D company. We really don't get any government funding, so we do everything to get what our customers need. Our team is an interdisciplinary group of team of scientists and engineers with some craftspeople to allow us to do it. You can see one of our machines in the picture here with our chief machinist, and then our building. We have a 45,000 square foot building where we work out of building these kind of tools. I should say too, we also do a lot of work in the military for various people to build specialty robots for them. So I'm going to turn now to the mining side. And I just wanted to put this up for terrestrial mining. In our world, ore is a mineral or chemical that can be mined at a profit. If you can't mine it at a profit, you don't do it. And so we essentially look for what's valuable, and we need to understand the volume and the values to be able to do our work. Our business is extremely energy intensive. If you look at it and you see, for example, the ability to take a rock that is a solid rock, drill holes in it, load it with explosives, and then crush it down to liberation size, which is the size to liberate the metal from the gangue or waste material. That is a very energy intensive problem. That stack and the sizing that goes on there takes almost the equivalent of our entire province's power grid to be able to operate. And so it is quite a unit. We run our own dams and our own electricity systems, and we did that not only in Sudbury, but we do that in other places around the world. A lot of the materials that we do in Sudbury, there's a total of 36 that range from nickel, copper, gold, platinum, palladium, to liquid SO2 and acid, all get produced here and are sold around the world. The plant I showed you produces all the liquid SO2 down to Mississippi, and that's for cleaning all of the food processing facilities all through I guess from Mississippi up is the northern United States. Our process is to go through prospecting and exploration, mine, mill, final processing, and transportation. We're a rail and transportation hub. Some of the biggest trucking companies in the world exist in our city. The big question as we go forward in our world is who's going to be doing the mining in the future, whether it's people or whether it's robots or a combination. That is really the big thing. People have an expectation of the cost of materials going down, and so we work on it. And my job inside of the business was to manage all the global R&D for Inco. So I was responsible for everything having to do with our future. I've subsequently left Inco and took on a position running Penguin and held a research chair for a while, and now I'm a professor at the University of Alberta as well. But my main focus is in Penguin. So we basically do as much in this ore body to fill up as much of that periodic table for everybody that you could imagine. We produce bismuth, some of the rare earth minerals around here, as well as the straightforward nickel, copper stuff. Like I said, about 36 minerals and metals, chemicals. And then I wanted to put this up because this is basically the Earth's crust and where we do it from. If you notice, you don't see nickel on the chart, but we happen to be sitting on an asteroid hit, and that asteroid hit is about 60 kilometers by 40 kilometers in an elliptical shape. and all of the minerals and metals are around the edge of the hit. It is one of the top 3 ore bodies in the world. It's been mined for the last 200 years seriously, but it's been mined by the natives for a lot longer, and it will be mined for many hundreds of years to go in the future. The difference, as I said earlier, was it's whether it's going to be mined by people or robots as we move into the future. I just wanted to put this up for 2 reasons. One, to show you where we go. We, like you guys at NASA, go to all the corners of the world where you're trying to go to the corners of the universe. I've been in mines where you have to fly from where we are to a small little airport, to a float plane, to taking ATVs out to the site. One of the places I've been is up off the edge of Hudson's Bay, and it is not a place that people want to go to. And it's even harder to get energy to it, where we try and get power and facilities to it. The other thing I want you to realize is that 71% of the world is underwater, and there's basically no undersea mining going on yet. There's one property in Papua New Guinea that they're working very hard to try and get in play, and there's a couple of very small operations. But I fully believe that the work we do in this group of us and you guys will enable undersea mining as we go into the future. And that's, for me, a big advantage as we move forward. So terrestrial mining is currently done in 2 ways. Surface mining, where you get a scale of 300,000 tons per day plus, with large shovels, trucks, and crushers. The trucks range from 100 to hundreds of tons. I believe the biggest one in the world today is approaching 500 tons. An underground mine, the scale goes down significantly to more like 10,000 tons a day, although there are some mines that are bigger, but it's much smaller equipment with drills, explosives, diggers, haulers, that range in kind of size to 10 to 70 tons. And then as we move forward, this future undersea mining, we don't quite yet know the scale of it and what we're able to do. But there are some promising areas in that from a environmental point of view that are counterintuitive. And if we want, we can talk about those a little bit later. The one thing that all miners worry about is gravity. We do everything with gravity as a consideration, and I'll talk about that a little bit more. So those fundamental approaches have been shifting to manless mining, which has been the basis for my career over the last 35 years. It's a constant journey towards that. When I first started in this mining company, there was 25,000 people working here, and now the company works at a level of about 4,000 employees. So, and producing the same or more output. So the job is to make the personnel we have safer, more productive, produce higher quality, and shift from being the guy in the coveralls to the guy in the shirt sleeves for knowledge-based jobs. So I want to show you a little synopsis of things that have been done over the year. When when I first started my career, there was no communications in an underground mine. And so to give you an idea of what no means, we had guys with wrenches tapping on pipes for doing Morse code type work. So you can imagine that trying to automate an environment with absolutely zero communications and networking would be near impossible. So I got my doctorate in figuring out how to effectively get 500 megabits per second underground everywhere in the mine, so that we could begin to look at how we would have small robots operating. The second part of my thesis was, what would that mean from an economic point of view for mines in the future? And that showed that this approach was one of the only ways to allow these mines to continue to be viable in the future. Along the path at that time, I was involved in building the first autonomous haulage truck that went into Little Stobie Mine. So you can imagine that it went through 2 years of continuous operation with no personnel on board in 1989 and to 1992. That's, for everybody in this room, probably almost 10 years ahead of the DARPA Grand Challenge from LA to Las Vegas. And so I was asked to participate in it, and I didn't do it because I had a regular job to do. That truck was a 70-ton haulage truck with a 70-ton payload. And it moved over its lifetime 3 million tons of material with literally no breakdowns. The next thing we did was we did a demonstration of running LHDs, which is our front-end loaders, from a surface control room in 1992. You can see in the picture on the right, that's me in the green suit on the right-hand side. My operator was a guy by the name of Chico Villanov, and he's in that blue chair. Those screens were set up in downtown Toronto, and the two machines that he's operating in the center two screens are 400 kilometers away in Sudbury. He ran both machines, getting a productivity improvement of 200%. Subsequent to that, we ran as many as 3 machines to be able to do that work. Around that time, we also were running drills from surface, and those drills, you guys came to visit my facilities. A guy by the name of Brian Glass was one of them, to make a determination of whether you could drill off the planet tele-remotely, because we were doing it in practice on Earth on a regular basis. And so it helped you guys make that decision. With the demonstration of running the scoops, we started a program which I called the Mining Automation Project. It was conceived in 1993, and I ran it as a 5-year project for the company. It consisted of people from Canadian government, the US government, Dyno Nobel Explosives, and Sandvik out of Sweden, to build a suite of mining equipment to allow everything to be run from a surface control room with no personnel needing to go underground except for maintenance. And I'll talk a little bit more about that in a second. This is the logo for the Mining Automation Project or program. And what it depicts is a head frame, which is the triangle and the curvature of the Earth, and then a button, which is an elevator button, and the slogan for the project was "Going Up." The consortium was led by Inco, Tamrock, Dyno Nobel, and the Canadian government. I ran a research mine from 1995 to 2001 with the objective of creating a telerobotic mining pilot project. And so in the mining operation, everything we do is about proving and de-risking. And so we knew we were able to do it, and then it was to put it in an operation and compare the timing of the various unit operations against what we were doing in the current operation by benchmarking. A second economic feasibility study was completed, and it showed that our costs would decrease by about 70% by implementing a robotic operation. And we would get back approximately 5 to 6 hours a day, because we were losing that in travel time. So with the two economic studies of the two mines, we started working on implementing pieces at various mines. So one operator running 3 long hole drills has remained in operation now for, it's no longer 25 years, it's more like 32 years. The technology was 90% complete, but our mining culture, combined with Inco's financial decay, halted the project. And the project ended up getting sold, the operation ended up getting sold to CVRD, which is a Brazilian company now called Vale. About that time, I decided to leave Inco and go into the university system and start Penguin. And so I'm gonna now, so Penguin was established to continue the work in the field while the mining culture was moving its way along and getting it to a place where we could implement things. I took on a role in consulting, in which I do for many mining companies around the world. The first area that we worked on was to get and take all of the technologies that had been worked on and continue to advance them for the next generation. And so Penguin then began a process of patenting and research that allowed us to work in these particular fields. So one of them was in wired and wireless networking technologies that included our patented Li-Fi systems. We've been working in the area of Li-Fi technology now for nearly 20 years and have systems we've delivered to the field. We also have been working in GPS and non-GPS environments. We've modified military positioning equipment to work in underground mines, because you have to change the mathematics inside of them to be able to get them to work properly. And we have no GPS underground. We also work on very high capability computational platforms for machine control and data collection. And we build robot systems or modify current mining machines to be robot systems, and spend a lot of time building those and building them up for people, as well as teleoperation control centers. And I'll show you just a few slides on our foundation technologies. We were asked to work on the idea. So with my PhD being in basically using wireless radio communications and being able to accomplish that for many different robots simultaneously, that was not good enough for some of the open pit miners, because you would begin to infringe on frequency distribution charts for radios because of the bandwidth that was going to be required for full motion video to operate the machines. We knew we would be able to do some work autonomously, but we also knew we would need people to operate some parts that we had not automated. So we began to work on optical communications. You can see some boats up here and some of our prototype optical comm systems. The original units were multi-faced LEDs that allowed us to transmit at 1 gigabit per second, and receivers like this one that have been patented, which allow us to receive information from a wide variety of angles because robots move around. We did all this work underwater because we were limiting bandwidth to be able to get high intensity light in operation. And then we put all this available onto current robots that we were working on. And I'll show you a couple of videos of that information. This is a video of a simulation inside of the building. All of this was supported by your National Science Foundation. We were able to combine and get specialty displays with robots. This robot actually worked underwater, but it was very difficult to show the process underwater with videos. So we put all the pieces up in our facility and did the work. We also then took the same equipment that had been tested in the ocean and put it on one of our robots to see how it was going to work in a surface application. And so in the surface application, we have achieved at that time 400 megabits per second in full daylight. And so you see the robot being controlled from the unit that was mounted on board, the yellow piece, and the optical system behind it. This particular unit testing was done several years ago, and now we have some commercial product in the mining industry with these optical systems on it. I talked for a minute about working in non-GPS environments. We have taken military plan systems and put Penguin proprietary triangulation systems with them and rewritten some of the code inside of these units so they'll function in an underground environment. We combine that with the laser scanners and can accomplish some very interesting mapping techniques. This is the control systems we now use on our equipment. It has the embedded controller for running the positioning systems, as well as the ability to go out to our different telecommand units as we move forward. So now I want to show you a couple of pieces. Mining technology is going through a major transformation, as I've been talking about. Networking and positioning are crucial to it. Artificial intelligence with advanced sensing, pattern recognition, emulated reality, robot coordination, and cooperative robotics. I have to say, in this picture, there's no published papers on what you're seeing in this picture. The reason there isn't is there was a major mining problem that occurred, and the problem was that 600 holes were drilled and loaded with explosives that amounted to 360,000 kilos of explosives. The ground underneath was hot, and what occurred because of the heat was one of the holes went off prematurely, nearly killing a couple of people. So Penguin was was searched out by the mining company to build a cooperative robotic system that would go out and do two things. One, be able to go out and assess the 600 holes for their temperatures and provide that survey back without going in the danger zone, which was 600 meters away, 3 kilometers as you drove, but 600 meters as the crow flew. And then have the systems, robotic systems, ready to drive the 3 kilometers every day and auger out the explosives and put a picking robot down to pick out the primer and detonator. So the 3 robots you see in the picture, the one on the left-hand side is our communications sensing robot, and it's on its way out to the site, where the other 2 are the auger robot, where the mast would go up, and the picker robot that could reach down the hole 30 feet and pull out the primer and detonator. All had inertial systems on them combined with GPS for high accuracy. I'll say at this point, I can talk to you about the technology. I can't talk to you about the mine, and I can't talk to you about the results because I'm bound by confidentiality agreements to do that. But I wanted to show it to you so that you got a feel for where the industry stands in terms of robotics and telecommand systems. By the way, this control center was inside of a CCAN, and we had 5 CCANs dropped into the middle of nowhere where we put in satellite uplinks and 5 workstations for operators, as well as latrine and all the other facilities to stay on site. I will say to you that this camera that's on here is a thermal imaging camera. We turned on the robot at night and there was a family of grizzly bears wandering around where we were. So it was very easy to convince all these young guys to put their lunches into the fridge inside. Again, what's driving the change? Mine-wide networking systems, really telecommunications, and our ability to move from RF to Wi-Fi and now Li-Fi systems. Industrial computing systems are increasing in capacity, and our human-machine interfaces are getting much better. For us, without having the ability to determine subsurface position, doing this kind of work is very difficult. And we've become quite good at situational awareness systems for what we're doing. And then obviously artificial intelligence. Now we're starting to get huge gains in looking at patterns that we see and being able to assess performance of swarms of information, swarms of robots gathering information, and then robots and droids. I'm going to show you an example, robot mapping. This is a typical mapping mapping group on surface. We're now able, with our little M3D2 robot, to do full mapping, gathering 300,000 points per second, thermal imaging, full scan views, and using differential GPS and inertial systems inside in combination. This slide is a picture of one of our original mapping units that was put into operation in South America. We were asked to be able to rapidly map an underground area. So we went in and used this robot with its laser scanners and long 3D scanner, went in and mapped that entire area in about an hour, put it onto their CAD systems, and then built a 3D version. And I'll say to you, this is done around 2010. And I'm going to contrast it with the one I'm about to show you. The reason we had two robots is that, again, this was a telecommunications robot, and it was the link between this robot. So we could build basically a daisy chain of comms robots to get as far out as we wanted to into the mine where it was dangerous. So now we've enhanced the capabilities in what we've been doing, and this picture here is a survey we did of an underground mine last year, and you can see the level of detail we're now able to get in subsurface environments. We can even travel through the rock to the other sides and look around. In here, we can do geologic assessments and ground support assessments, drift location for stress analysis. We provide that in ventilation assessment, and overbreak and underbreak. And these form the basis for new mining machine control.
Greg, can you take a question at this point?
Can I? Sure.
This is Dave Huntsman at NASA Glenn in Cleveland. The example you've shown so far is related to systems that are on wheels doing the surveys. Have you used that assumes, or it looks like assumes, flat surfaces or relatively flat surfaces that they're able to go along? Have you been able to use flying droids or RPVs or whatever that are a bit more flexible, where such things aren't available yet to do the same thing?
Yes. So the reason I've shown mostly flat stuff is because we're using these military INS systems, and for us to get the accuracies we need underground, we need those systems, and those systems weigh about 150 pounds. And so we've kept them onto those units that are drivable, but we have new systems that are all tracked for taking very difficult terrain in the mines. As the quality of the survey tools, not the quality, but the size and the weight drop, then we'll be able to work our way into drones. But for us, the accuracy is more important. We need to know not just that there's a picture there, but that each point in that picture is geolocated within a few centimeters. And
okay, got it.
And so what we're doing is making sure. So if you look at that picture that I'm showing you there, those rocks, I could tell you exactly the X, Y, Z pitch, roll, yaw coordinate of that rock in three-dimensional space.
Dave, this is Brad. I'm going to encourage you to think about the fact that Greg has actually got a lot to say about lunar mining later in this presentation. So I think that what you'll discover is that you might want to schedule him to come back for one or more additional follow-up conversations, which there's a lot of really good material here.
I bet. Okay, thanks. Great.
Yeah, no problem. So with that kind of mapping, we've begun to work on new tools. So everybody here will know what a CNC machine tool is. And what we're doing now is making mobile CNC mining equipment. So because we have such accurate X, Y, Z pitch, roll, yaw coordinates, and we're building our own arm models with kinematic control, we're able to place machines and booms within the mining environment exactly where we want them. And so having scanned in an entire underground mining operation, we have kinematic models of the unit that you see here that can fit inside the mine. Now, I want to describe this to you. This is a robot that is a 6-ton robot. It's an 8-wheeled unit that can basically climb over 1-meter chunks. It has 4 cameras on board and an arm that reaches out 15 feet and up 30 feet with a drill on the end and the ability to load explosives on the very end of the unit. It's all controlled through a combination Wi-Fi, Li-Fi system. And you see the Li-Fi system, but the Wi-Fi system are these 2 nodes up here. And so we use both in combination. This job is a job that has been done by people, and the people do it with a bamboo pole and explosives taped on the end and put themselves in harm's way on a daily basis. And so a major mining company asked me to sort out how to get a robot to do the job, because their volume of times they were going to have to do this was going from 10 a day to 1,000 a day. It's very dirty, dangerous, and dull work, which is perfect for robotics. The entire system now with the robot, the command center is in here in the back seat, and we have an optical transmission system to match the one out here with these 3 Wi-Fi antennas that allow the 2 units to communicate. This robot is a battery operated robot with 135 horsepower in it on peak. It has the similar batteries to what is in the Tesla inside it, with the charging unit on the back of this machine. The truck was selected because it was a hydrostatic machine, so we could charge the batteries while it was driving, and be able to move around the mine. Now, I want to say, and Brad's right, like, I'm showing you single slides. This is the culmination of like 35 years of work. I could show you about 3 hours of presentations just on this robot and the robot system. This is the command unit. Consists of 3 displays. This is the picture of the unit drilling the holes remotely outside. And now you'll see the unit rotate, and we put in the explosives into the hole and back away with the leg wire. But the operator has all these various views to be able to accomplish that task and make sure everything's in place. This is our next step. Sorry. That scanner was scanning an underground environment. I didn't have the picture for it, but we put that into a gaming model, and then we have a kinematic model of the unit that goes in for setting up the machine. The operator in the future is actually going to run the gaming model, and the machine will emulate what the gaming model says to do. The reason for that is that we can then get accurate information about what the area where we shouldn't go is, and the robot can work inside of that environment safely without any personnel being exposed. And so I'm just going to show you one of the areas that we're currently working on with the mining company. And it is, the reason that I'm going to show you is that this machine is also part of something that we considered for mining water on the moon, underneath the crust of Shackleton Crater. Now that you have all those technologies together, mining companies are asking me to build this kind of a unit. What it is 5 drills across the top on this track base with an area to plow and make level, and then a geosensing system on the back of the unit. So as we move forward, we're doing an analysis of what the grade is for for mining. And I have, like I said, several hours of presentations that's been done for the mining companies that I could show you, but this is the best representative picture without getting into a 10-minute long video. So what does this mean for mining in space? If that's where we are terrestrially, what are we going to do? And the lunar mining concept I'm about to show you has been developed really between myself and Brad and some of the people at the Canadian Space Agency, and a few others from various perspectives. We've had input from people at Shackleton that were sitting around the table as we presented the concepts. Some of the concepts are showing up in the off-world group, but this is the original presentations that have been done. And I'll say this is done from a mining perspective more than from a space perspective. Space excavation and mining techniques are going to end up being informed by what we're doing. So the idea of teleoperation workstations is not a new idea in the mining industry today. The ability to get various pieces of mining equipment to the moon or to an asteroid or to wherever else needs to be thought through quite substantially, given some of the constraints that are in place. I projected with the Shackleton group that what we would end up doing is creating a base that would be an underground base on the moon. The reason for that is some of the issues around radiation, temperature, gravity, and things that guys like me take into account when you're got to go somewhere to mine. You know, I would do the same kind of analysis, for example, in mining in Arctic conditions, and what would we have to do to create areas. One of the operations we made, people just literally don't go outside at all. And so the whole thing is an enclosed space. In this case, I used, because of what we were doing, the idea of water, but this can be put in place. And a lot of these people that I put in have had significant input into this design. Jim Logan, especially from the point of view of radiation, and Bill Stone. Brad and Tim Joseph is a mining expert with me, and then some of the other guys that you may know or may not know. So some of the issues that I take into account as a mining engineer was we need data from exploration work, because we would not go and put any property in without, first of all, doing a complete kind of prospecting analysis. Gravity at 1.6 is an issue that is substantial that we have to deal with. Radiation is a much larger issue than originally thought by NASA, and I've got a graphic that Jim Logan gave me. mineral right now, which is water, is located in permanently shadowed regions of the crater, which causes some very significant problems for the release of water. And Brad is probably better at talking about that than I am, because he'll know more of the details. So lunar mining will require much more massive equipment than terrestrial mining, just due to the gravity issues, and getting an equivalent of terrestrial forces to the lunar crust. That comes along, and I don't have it in there, but when you have the levels of dust that I know are up on the moon, as you're getting that kind of tractive effort, you're going to create a lot of dust. We spend a great deal of time in our own industry watering and compacting and doing all the things we have to, and we have some unique approaches for dust control that are proprietary. Radiation will be required. You need essentially the equivalent of 10 meters of water, which turns out to be 4 meters of rock, to be able to protect people. Crater temperatures are minus 230 degrees C or less. So we understand the best mining equipment in the world today works with the current metallurgy at minus 60 degrees C. And we can break pieces of end effectors off regularly. Water vaporization will be an issue. So somehow that had got us away from the idea of strip mining, because we thought that was going to be a problem. And water will be liberated. We don't know how water is going to be liberated up there, because we would typically do it by sizing. But if we get water, we don't know how it comes. We don't know if it comes entrained in rock, or if it's adjacent to rock, if it's ice or whatever it is. There's a complete unknown around that. So this is one of the challenges of lunar prospecting, is in this graph. This graph was Jim Logan's graph that showed radiation that occurred during between 1968 June and December 1969. And the red arrows represent Apollo missions. And so these are radiation events, and you can see that there were some very significant radiation events that really weren't dealt with properly and needed to be dealt with. And then the same thing, gravity and lack of atmosphere. So I'm going to show you a notional idea behind how to establish a lunar base. I think it was Bill Stone who said to me that the lunar modules that had landed when I forget which missions, you guys will know them better than I do. A second lunar lander went close to another one and started a sandstorm that turned out to be more like a sandblasting exercise. So we looked at a landing area close to this lunar portals, and then started looking at how we would build up an entranceway into the solid rock. This is what we first considered as an initial foothold. A couple of things that are a little bit different from my perspective. I took the approach that we would need to have an H2O lock as opposed to an airlock. That's more for radiation purposes, but there needs to be a way to manage that to get people in and out of this area and equipment. We had a larger portal for equipment and a smaller portal for people. We had 4.2 meters of rock protection against radiation. And what we would do with our mining equipment is use wedging inside to emulate gravity. So by having the pieces, the robots wedged inside, we could then emulate gravity and get normal forces like we get on Earth to construct. We would need to find a way that temperature could be managed. It was very cold. And so that's an area that would be required. But we could pressurize the underground excavation so that it could almost become, I wouldn't call it a shirt sleeve environment, but at least a non-personnel protective environment, short of temperature. We knew we would need a bunch of pieces in there, front-end loaders, a main portal structure. We believed we could build our locks on Earth and bring them in, and that would be the only two pieces. But then we would need to manage food and water and how we would tunnel. We have techniques, which I'm not going to show you, about how to tunnel that we put in place. I want to say in my world, I was responsible for 30 diamond drills that did nothing but go and look for ore around the Sudbury Basin. And so I've not only responsible for the operation of them, I've built them and built some of the probes that we would put in to go and do that work. You'll notice in all of this area, this is essentially a core analysis system. As you go in, we had built a drill, which we called a guided drill. And it essentially worked like a small inchworm. To do a proper drilling mission of any scale, you're going to have to drill more than a meter into the surface to be able to look at what's underneath. And the forces that work in that are going to be required to drill as if they were on Earth. The unit we built in guided drilling, since it worked like an inchworm and used the hole that you develop, we could get a similar drilling system for the moon as to what you would have on Earth for long hole drilling. And so that's where this essentially comes from. The other one is that now several ore bodies have been found around the world using neutron activation probes and another technology that's called cross borehole telemetry. I got that wrong. Anyways, what it does is it puts sound waves down one side and receives the sound waves in another, and instead of getting a point, you get a plane of information.
It's a tomography.
Thank you, Brad. I'm just missing the word. So we looked at this and being able to have a pair of these units so we could do neutron activation probes and cross-borehole tomography if we're going to do anything on the moon. These were just sites, so we had to consider how far we had to move things. But that's, and then we considered how we would look for lunar water. We would have to determine the qualities and quantity. I approach this like you approach a mining operation. So before we go anywhere, we need to know quantities and quality and the mining set to be able to set up and begin to understand how big and small things need to be. And so that would be our objective in doing this. With prospecting and what we've done on Earth, we would end up having, at first, a ground-based Earth-to-Moon teleoperation. We believe that that's feasible. I did some work a while ago with you guys in one of the university competitions, and we proved that we could manage a 3-second delay, and we've done it on a regular basis inside of the mines. Latency is a huge issue that we spend a lot of time sorting out. It's also why we've moved our way into optical communication from radio and tried to divide streams and do the things we do. But when we did the demonstration that I showed you way back at the beginning of the presentation, we had a 35 millisecond round trip down and back to the controls. So we also know that most mechanical devices can be managed quite successfully in a 150 millisecond control environment. So we're able to do that on Earth, and we'll have to sort all those things out when it comes to the moon. I showed you the optical system. I believe the optical system is going to play a huge role in what's going on with you guys and with us in the mining industry. I put in actually to go down to one of your optical things in next week, but I'm not allowed to go because I'm not a domestic national to the United States, even though I have all this optical work that I've been working on for 20 years. But I was told I'm not allowed. So if anybody here can do anything about that, I'd love to help you, but it seems like NASA doesn't want me to be involved in that. So this was the sending of the 2 robots, getting it out and being controlled. And then now I've just put in a little bit about what we would do afterwards. I have a suite of equipment that we've developed as part of the Canadian Space Agency work. This is one of the units, which is like a robotic front-end loader. We are doing a lot of work in chairs and control chairs. Interestingly enough, we're not only doing them for control of machines, we're doing them for helping Alzheimer's patients and others, using some techniques in neuroplasticity to be able to allow people to run machines using those kinds of techniques. And I can explain a lot about that over time. And like I said, there's a whole fleet of equipment and mining techniques that go together to be able to tunnel and do all the pieces of work. Those, I think, will be able to develop a short-term base and get us on the path to get water underway. Terrestrial control doesn't look a whole lot different than your current mission control, other than these units here. We had talked a while ago about putting one of these units on the ground and bouncing off a satellite and coming back down to an exploration drill to prove the concepts out, which I think would be a really good project to do. Or going from the space station with a unit like this back down to Earth for drilling control. I don't know where that got to, but we did have some initial discussions about it. And then establishing initial shelter with a water base and the ability to put people inside and eventually transform that into an on-site lunar control center with the mine working in it. And these are just some notional pictures that we put together to get a facility capable of human habitation and a portal for doing equipment maintenance. I'm not a huge believer, having been in the mining industry, in autonomous systems for doing this kind of work, just because we have too many wear parts on these machines that are going to have to be changed. I do believe that we can build machines to change the wear parts, but we're a little ways away from there yet. And all this is going to require power. I come from the camp of believing that nuclear power is the only way to go. I put it on my slides as long term. I actually believe it's going to be shorter term. but I know that that's a controversial subject. And then from this initial base and habitat, we would ramp down underneath the crater and then be able to pull the water into the crater if it's depending on its form. If it's entrained in rock, then I would hazard a guess that we can pull the rock in much like we do today. And you can see in here we have sleeping quarters as well as command centers for being able to run the machines. Storage of oxygen, airlocks for personnel quarters in case, sleeping quarters, personnel, a robotic mining center so that we can do some of that right on the moon. Latrine obviously is going to be required, and then a lunar telecommunications array. I'm not an expert in CO2 conversion with plants, but I'm sure there's a number of people in NASA and other places that can provide more information than I can on that. I want to just take a minute to show you one mining technique that we could apply quite easily on the moon. There's several that I could show. I just did this one because at first we considered that the water may be a large bulk area of water. But if it was in the bottom of a crater, you can essentially create funnels and have the material self-break on top of you. That kind of rock is likely to be, if you undercut it properly, will self-break and fall in, much like it will on Earth. And then if you put the right locks in place, you can do this all bringing the material in without anybody needing to wear specialty equipment. Obviously, again, gravity. So you have to consider in the mining method, because gravity would need to, you would need to get the idea of 1/6 gravity and understand the implications for the entire bottom of Shackleton Crater, or anything else you were going to do. Wedging of equipment to produce water and how you're going to do that, you know, what the thickness is. I mean, these kind of things for me are so speculative only because I don't know what form the rock is going to be in the water, and that's why the processing mission is so important.
Greg, to answer that question, I just spent 3 days recently at a lunar volatiles workshop. There's a lot of scientific knowledge to add to this. So more work to be done, but stuff is getting revealed.
Yeah, once we know that, like I know all the methods and all the methods that are out there and what we can apply and what we can't. It's just a matter of knowing what form it's in. And then obviously processing has to be done, and we'll be able to look at that. So in summary, we have an initial an initial plan, and based on what Bill Hesterlid did and what I've done and what we put in place, there aren't any real showstoppers for building a mine on the moon. And I think it makes a lot of sense to build a mine on the moon given the gravity well that the Earth's in. But I will say to you that in my world, I talk a lot about de-risking. And one of the things that we've developed up here is a way to create a space mining test facility. The rock in Sudbury is so hard that we could actually take the, I don't know what your neutral buoyancy facility that you have in the States. I could build one of those big enough underground in the rock here to put the entire space station in, as well as build an underground equivalent of a mine on the moon running underwater with all the different pieces. And so we have some quite developed plans for doing that, and are really interested in making that happen to de-risk anything that's got to occur before we go and actually do it. And so with that, I'll thank you and take any questions that you have.
Greg,
Yep.
this is Doug Plata.
Yes.
Are you able to hear me well?
Yep, I can hear you perfectly.
So Anthony Colaprete is was the principal investigator for the L-Cross mission,
Yes.
which really confirmed water ice in the permanently shadowed craters of Cabeus Crater.
Sure.
If you were to speak with him, I think perhaps your plans might change considerably, because it seems as though the water ice that they discovered, and this was 5.6% by weight, so that's 1 part per 18, so pretty high ore concentration of water ice. It seems as though it was not in solid rock, like mining on Earth typically is done.
Yes.
But the data, the best interpretation of the data is that the ice crystals, the pure ice crystals, were in fluffy regolith. Just because of the way the ejecta came out, it seems as though it was not solid, it wasn't hard, it wasn't permafrost, it was fluffy regolith, sort of little crystals in dust.
Okay.
So I guess I'm fundamentally questioning, it seems though you guys think from terrestrial mine perspective and talk about needing to crush rock and working underground and these sorts of things. I mean, just within the last few weeks, 2 weeks, something like that, we have a study coming out that shows that there's actually ice actually on the surface in these permanently shadowed craters throughout the South Pole region. So I'm really looking at shallow excavation of fluffy regolith, and so I just don't think that the typical approaches on Earth, which you're going for ore that's very small concentrations, and in fact these are like metal veins in rock. I'm not sure that really applies on the moon.
Sure. I mean, we in the equipment suite that I put together, we were taking into account if you had to go underground or if you had to do it on surface. Mm-hmm. And one of the pieces that we have in there is what's called a scraper. And a scraper is something to go after it if it was in crystalline form and it was small particles. And so we just didn't at the time know. And so we kind of went down a couple of paths in trying to do it. I obviously don't have the advantage of knowing any of that information from you guys right now. But I would think differently if that's the way it is and how to process it.
Well, maybe I could put you in touch with Anthony Colaprete so he could explain to you himself what he thinks the environment is on the moon.
Sure, that would be great.
Yeah, let me chime in here, Doug, for a second. This is Dan Raskin, and Greg, yeah, I found this fascinating. And I think, yeah, the things that you pointed out, where we're at right now on the moon is really what we call the prospecting phase. And that's the area that we've been trying to get some more specificity that, how many locations do we need to look at? What type of data do we need? You're exactly right. We need that first to be able to have a more sensible and thoughtful way of how would you actually even do resource extraction. And I think that the prospecting phase needs more attention. And I highly agree that power is going to be the critical for transportation followed by power. If you can't get there, you can't do anything. That's the transportation. But once you can get there, it's clear that power is going to be critical, and particularly another factoid of the lunar surface, you have the lunar night where things get really cold. And if you can't survive the lunar night, that's going to really impact anything you can do.
Sure. I mean, just so I've said it, I've seen every kind of mining method from small scrapers picking up gold nuggets or gold pieces to large scale potash cutting machines and coal cutting machines, to drilling and blasting for vein following or for large bulk, low concentrated samples. And we just don't have a clue yet as to what that is. And you know, if it is small particles and it's mixed in with a bit of dust, then we're gonna have to figure a way to melt it out or do something. If it's not, then we have to take that action. All I know, like you said, Dan, is that all those things require energy.
Yeah.
One of the things that you should add to your slides, Greg, this is Brad, is the machine that we built for the NASA excavation challenge contest. It was basically designed after a hag loader, and it went after granular materials, and it would load it really fast. It's the perfect mining system actually for solving the granular material problem that Doug was mentioning. If the lunar polar materials are actually that type of granular material, the reason that we didn't win that contest was integration issues. It wasn't a good design or completion of the active machine. So there were some operational challenges that came up, but it's a really slick design, and one picture I think would demonstrate that, Greg, that you've taken that beyond engineering design all the way to hardware development and testing.
Yeah.
Hey, Brad. Brad.
Yes.
This is Doug again. I know what a bucket wheel excavator is, but what's a hag?
Doug, I would like to maybe ask you a question, which is one of the driving questions behind the decision we made in 2009 to really design an underground lunar facility, and it was really designed more for humans than for the mining equipment. The mining method was sort of a secondary consideration. If you had this underground facility, what could you do to actually do mining from it? And that is, understanding that your background is actually as, coming from medicine, you're a medical doctor. How important do you think it is to shield humans on the lunar surface from the debilitating effects of radiation?
Well, I would place it as a pretty high requirement. But what I would say is, I really think that, from my perspective, you should have a crew in a shielded habitat. And I think you should bring the equipment into the habitat to where they can work in their own environment, and not necessarily.
Which was precisely what Greg has done, and that design work is actually scalable to peaks of eternal light. It's scalable to equatorial facilities. You can drive access to lava tubes. There are a number of applications of the mining technology that Greg has put together that go well beyond just mining the polar ice. This is, our original design was actually to start at the peak of eternal light near the top of Shackleton Crater and drive a tunnel all the way down underground, and then create access to the bottom of Shackleton Crater through a ramp from the surface of near the peak of eternal light. And that potentially is a feasible project given current mining technology. What is the amount of power it's going to take to do that? What are the other variables required to solve that design problem? Are really a matter of engineering, and I think we're close to having the right ability to do a kind of a project that could actually estimate that.
So what I would say is that I think from the power standpoint, when we talk about lunar nights, we need to think about where we start, and where we start is at these peaks of persistent illumination, in which the lunar night is 3 to 5 days, not 14 days. And you can go down to low power consumption operations during that time, and then as the sun hits the peaks of persistent illumination, you ramp up your operations again. I believe that the power limiting step is actually electrolysis, not so much the steaming out of the volatiles from the excavated, fluffy, icy regolith. What I'd also like to add is, for the temperatures, the cryogenic temperatures, there's a couple of things. Greg, you mentioned about parts breaking off when it gets cold, even like what, negative 60 Celsius.
Yes.
The parts, you know, aluminum. Take a look at the how aluminum performs at cryogenic temperatures. It actually performs very well,
Sure.
and we actually know this because the hydrogen tanks on the shuttle going through max Q were made out of aluminum. So aluminum my understanding is, does not become brittle at cryogenic temperatures. So I'd say any parts that are going to be that you can't have body heat, meaning that these things are like touching the surface and they're exposed to really the cryogenic temperatures, and you can't warm it from the inside. I would say those parts should be made out of aluminum.
Sure. It's the actual digging pieces though that are the problem. Like the strength in aluminum isn't there for us.
Yep.
Doug, you haven't seen what happens to aluminum in underground mining. It's very it wears out really quickly.
So I'm suggesting surface mining, in which you're going after the fluffy, icy regolith, which is what the L-Cross results suggest.
Well, and again, before we go down a design rat hole here, guys, I mean, you have to know what's there. And again, so let me pull it back up again to the prospecting. One of the things that we've seen is that, yeah, until you have an idea of what's there, you can make all kinds of plans, but probably most of them are going to be unworkable compared to what you find out when you get there and do the level of prospecting. And so where we're really at right now is understanding what's there in a way that is feasible given the realities of, you know, space transportation to the lunar surface and power and thermal control and things of those sorts.
Yeah, I think right now the key to it is building the right drilling unit.
Yes, the prospecting unit. Yeah, what is that? In fact, that if I had one question for you, Greg, would be that. Okay, what's the right prospecting unit? Okay, that can serve, you know, as a basis of maybe different types of prospecting. Keep in mind that in addition to the polar regions, we are going to be interested in off-polar regions as well. Okay, and there's some interesting things like the Compton-Belkovich thorium anomaly. There's some really interesting things on the moon. So we want to be able to operate more than just in the poles. We want to be able to operate, you know, in lower latitude areas as well. And so what would a kind of a universal prospecting vehicle look like? What would be its characteristics? I think you raise a good point. How do you drill when you're at 16G without having
Can I make a recommendation? Which is that Greg has enough experience with terrestrial prospecting and the design and development of custom drilling as well as mining equipment to actually probably give you a 1-hour lecture on just that topic alone.
Well, actually, thank you, Brad, because what I was thinking, in fact, we're going to have to cut this off here because I've got to run, but I found this was fascinating. And maybe what we can do, Greg, is have you come back. And what I would really personally like to see, and I think Allison's on the line as well, Zuniga, and we really need to understand better what's the initial prospecting vehicle to get this critical initial data about, you know, what are the resources of interest, including water, what's the state of the lunar surface, what might be some viable ways of actually pursuing some extraction methods at small scale, because you'd be starting with small, you know, laboratory type scales. And I don't know if Allison, if you want to chime in for a second on that.
Yeah, I'm here. Yeah, excellent presentation, Greg. Yeah, fascinating. And I agree with exactly what Dan was saying. We have to get ground truth data. We definitely need to put a lot of effort in the prospecting phase. And we definitely don't just want to look at the poles. There are other areas of interest. So, yeah, if you would like to come back, maybe we can work with Lisa and find another time when you can come back and talk specifically about prospecting, the equipment that you need, not just focus on water, but also other metals that you can find on the moon and in other areas. I'm sure you've got lots of, like you said, lots of plans, and we would love to hear that.
Yeah. The one thing that I just want to ask the question of, and as you talk about this, one of the things that I seemed to run into before was people thinking that regolith was all there was on the moon. I don't believe that at all. I believe that underneath the regolith is going to be something equivalent to Earth. And right now, plans for drilling seem to be all very short. And you really need to have a drilling program with long hole drilling to understand what's there. You know, we would not consider an ore body defined at 2,000 or 3,000 feet of drilling down. We would just be looking at it and saying, oh, we found something. Now let's go put a bunch of holes that long all around it to create something.
Well, see, one of the issues that we have, which again, I think you can be very helpful with, NASA has planetary scientists like Tony Calapreta. We don't really have resource scientists or resource engineers. And see, and I actually, years ago, did an internship with Conoco Oil Company out in the oil patch. And so I have an idea of what resource engineering is, and we don't have that at NASA for the most part. And that's where and so even some of the scales of like how many data points do you need and to what depths and so on are often, you know, way off by orders of magnitude compared to what you actually need to do. And I think that's where it would be, I think, very helpful to get a real mining engineer's perspective on the type of data you would need to essentially lay out, you know, an ore body or a resource zone to have some reasonable expectation of what you could do with it. Versus a more of a science-based planetary scientist view, which is largely what NASA's been dominated with.
Yeah, that makes perfect sense to me because that's what I felt in all the different people I've talked to up to now.
Yes.
I felt like I've been fighting against that science-based approach. And
Right.
it's like, you know, the Ontario government, as an example, has a huge database where they've done the entire province, and they go around and fly magnetometers, and they fly all the various things, and they fill up the entire database to understand what's there, and then you pick drilling targets.
Yes, yes, I know.
And you go out and pick the drilling target. You say, this has the most promise. Let's put a hole here and then see. And then you wait for the next one, the next hole to come in, and you go, well, okay, so we didn't find anything, but it's still a promising target, or we found something. We really need to drill it longer or over here or there or whatever. And that, to me, is what's been missing on the moon and even on anything people are talking about with asteroids.
Yep, I would agree.
There's no idea. And you know, one of the other important things is that gyro system I've been working on, it changes, all the math changes when the diameter of the planetoid changes.
Yep.
And so I've been going inside and managing how all that changes. You know, because if you want to run it in a mine, when you go underground 2,000 feet, those kind of systems don't work because you're 2,000 feet underground.
Yeah, no, I can really appreciate that. So, yeah, I think these are all really good questions. So, tell you what, let's do that. I've got to cut this off now, but why don't we do that? Let's arrange another time for you to come back, Greg, because I think we have a lot more we